Our first experiment involves chromatography. Chromatography is a method to separate components of a mixture, but sometimes that's not the point of what you're doing. I mean, sometimes, yes, you're trying to like purify one component of a mixture so that you can obtain it for some reason. But sometimes the purpose is to identify a specific component of the mixture or to identify the mixture itself. So you've probably seen chromatography somewhere before. It's very common. Probably all chemistry labs do some kind of chromatography. But where you may have seen it, if you haven't seen it in the lab, is on like a crime show. Maybe you've seen something where they show you these plots or graphs where you have lines with peaks like this. And I did one and say they look at this and it gives the pattern for the gasoline that was found at the scene of the fire, and then they run an experiment on the gasoline that was found in some person's garage, and they say that these match, and so they must be from the same source. And so they're matching the mixture. They're not really interested in the fact that they separated the components to do that. Each of these peaks, by the way, would represent a different compound. But anyway, so the point is sometimes you're trying to identify something when you're doing this separation. All chromatography involves a mobile phase that moves. It's a fluid. It can be a gas or a liquid. It moves through a stationary phase. The stationary phase often seems like a solid. It could be a solid, but sometimes it's like a liquid that's stuck to a solid. So anyway, we'll look at some examples of those. And elution is the process of, as the mixture gets separated, what's going on. So let's look at an example of these. Some common types of chromatography are gas chromatography, high performance liquid chromatography. Column chromatography is something you might do like in biochemistry. Thin layer is on a plate, like on a slide. It's the most similar to what we're doing, the paper chromatography. But anyway, let's look at the GC. So you'll have some kind of tube, and then this tube will be packed with some kind of material. It may be beads, or it may be like a sponge-like material. There, I got that pretty full. Okay, and then, you know, so this tube is, we would call it a column. That it has the beads that we're seeing here. They are the stationary phase. They are not going to move. And then what happens is you push a gas through there. We would usually use something that's like a noble gas that's not going to react, like helium. And the helium's going to go all the way through and out the other end. And the helium is the mobile phase because it's moving. Okay, so this is kind of the setup of the equipment. But what you're going to do is you're going to add a sample, like you're going to inject a sample that'll go in the tube with the helium, and that sample, whatever that is, will go through and come out the other end. And the big question is, how long does it take to come through? Some compounds will take longer than others, and that's going to be a physical property of that compound. If you put a mixture of compounds into the column, ideally they're going to come out at different times, and from that you can identify them or the mixture. Okay, let's look at ours, but first up here, RF is for retention factor. This is going to basically be our way of quantifying how well the component moves through the stationary phase. And so instead of timing how long it takes to get through the column, we're going to look at where it ends up on our piece of paper. Anyway, I will do an example of that calculation in a minute. Two things you need to know about the RF, or the retention factor, is that it is unitless. In other words, the value is a number, but it doesn't have units, and that number is always less than 1. Okay, let's look at how we have our chromatography set up. So we have a piece of paper, and on that paper we're going to draw a line down here, and we're going to put some X's on here. I'm just going to do a few. And then we will spot our cations. Our solutions that we're using are metal ions. They're positive ions, so we'll put them samples down here. So we'll put dots of solutions down there, and then we will dip this paper into our eluting solution. And as soon as you do that, the eluting solution starts to soak up the page. It will move up the paper just by capillary action. And if it goes up over, which it will, your cations, then your cations will move up as well. So your cation will move up and end up higher. Okay, so in this situation, our mixtures are the cations that we put down here. Our stationary phase is the paper. It's porous and it's just sitting still. The mobile phase is the solvent, which is the liquid we put down here. We also call that the eluting solution. And the chromatogram is what you end up, after it runs, after it elutes, you end up with a pattern of spots. Let's look at one of those. So this is a chromatogram showing where the different cations ended up on the paper. And so a couple of things about chromatography. Okay, so let's just go ahead and to talk about this, let's just go ahead and say that we know that when we dipped this paper in our eluting solution, we see where the spots went to, but I also need to draw where the eluting solution, we call that the solvent front or elution front. That's how far the wetness moved up the paper. Okay, and so you notice that two things. You notice that they moved to different distances. In other words, this iron moved way up here toward the top. It did not move as far up as the solvent did, but much more than the lead that stayed down here. And how far they move up has to do with their attractions. The cation being attracted to the paper more than the solution will make it stay down low because it's kind of stuck to the paper, and the solvent just goes right over it and it doesn't move much. Or if the cation is more attracted to the solution, it tends to move up with it as it soaks up, as it moves up. So how far up they move has to do with the properties of the cation of the substance. And what's neat about that is that it doesn't really matter if they start as a mixture. So like on our unknown down here, if we had a mixture here, each of those cations would move according to its properties. And so I can tell that this mixture has one component that moved like lead. And so its distance that it moved was not affected by the fact that it started as a mixture here, and we can tell what the other component was here. So each one moved according to its properties. They ended up separated, and we can identify. So this unknown is going to be the lead and the copper. Okay, so that's how you identify an unknown. Now let's talk about calculating a retention factor for something. Let me erase that. Okay, let's just do cobalt. A retention factor, you're going to measure the distance that the cation travels, and I'm just going to call it the spot. divided by the distance that the solution traveled, or the eluting solution. Okay, so we need distances. I've got a ruler. The thing you need to know is where is 0. And we draw this line here, and we start with everything on that line, all of our samples on that line. So that is our 0 line. On a quiz or a test, you need to know which one of these lines to label 0. Okay, so that is our 0. It's on our start line. And then I'm going to count up. Okay, and so if I want to do the distance that the spot traveled, what I'm going to do is go to the cobalt and try to go to the center of it and say what distance that is. That looks like 3.0 centimeters. And the solution traveled, so I'm measuring this for the spot, and then I want to measure this one right over that, and it looks like 7. Now for units, these are both centimeters, but we can see that that's going to cancel. So when we get our RF, it's not going to have units, it's unitless. So it's a good time to leave units off. 2 sig figs, 2 sig figs. And then remember, the other thing I told you is that RFs are always less than 1. And why is that? Well, the spot always has to have a smaller number than the solution, so this ends up less than 1. Because you can't have a spot end up above where the solution went. The solvent will always go as far. If the spot went just as far, it might be a 1, but that really doesn't happen. So one last thing I want to show you about RF and how it's consistent, a consistent property. As long as the solvent or eluting solution, mobile phase, stationary phase, temperature, conditions are the same, RF value is considered a constant. So let's look at a different example. What if I had a little piece of paper and I put a spot on it and I let it run, and let's just say for this sample, the sample ended up right in the middle, and so I would say the RF is 0.5. Okay, let's say I take a big piece of paper and I take the same sample and I run it again. Where do you think that spot will end up? Is it just going to be this short amount and be down here? Or will it be in the middle? And the answer is it'll be in the middle. Because how far it travels is always relative to the elution front, the solvent, how far it's going. Anyway, that should get you going on the lab.